So now that we can describe the relative angular motion between two reference points, we're going to turn back to our example of a spider moving on a Roomba and show how at this point we can define the position vector using two reference frames. However, we run into a bit of a snag when it comes to taking the velocity. So just to set the problem up again, we have our Roomba, a circle here, and the center is at point R. And then we have a spider at point S, and that spider can move in the radial direction along the line outlined here. And it can move towards or away from the robot center. And we want to ultimately find the acceleration of point S with respect to a fixed frame, frame A. And so, of course, in order to get to the acceleration, we have to first get the position and then the velocity vectors. Okay, so that's frame A. Ultimately, what we want is this position vector here, so ROS. But we have to write it in terms of the following two vectors, ROR, so the position vector that takes you from the origin to the center of the robot, and then this vector here, RRS. Right, and then once we know ROR and RRS, we can write ROS as the sum of the two. So R plus RS. So to define our OR, we say that it has some magnitude, we'll call it U, in the A1 direction, plus some magnitude V in the A2 direction. Now for our RS, we did the following. We said, okay, well, we know assume we know the orientation here, this theta value, so what the orientation of this robot is, as well as what the length of this vector is, R. So what is the distance from the spider, the point at which the spider is at, and the center of the robot? We'll call that R. And so then we can write RRS as R cosine of theta 1 A1 plus R sine of theta, I don't know why I wrote that 1 there, R of sine theta A2. And so with that, you can then write ROS as U plus R cosine theta A1 plus R sine theta plus V A2. So this is all, we had done this before. This is how we solved this previously. And now we're going to introduce how to solve or get a position vector using multiple reference frames. So again, we're just going to set the problem up in the very same way. So we still have our fixed frame A1 and A2, so, or fixed frame A here. Again, we have our Roomba, we have the center at point R, we have the spider that can move along this line, and the spider is at point S. And again, we still want this vector, ROS. We still want this vector, ROR, and we still need this vector r, rs. But how we're going to define vector RRS is going to be different. So, of course, ROS still is equal to ROR plus RS. And ROR is still going to equal some magnitude in the A1 direction plus some magnitude in the A2 direction. But now we're going to define, here's where we're going to define our second reference frame. So we're going to take reference frame B, and we're going to put its origin right at the center of the robot, so right at point R. And of course, we could define our unit vectors wherever we want, right? So I could put B1 here and B2 here. I could put them somewhere else, but for the sake of simplicity, you'll see why in a second. Sorry, I accidentally deleted my point R. Remember, this is our RRS vector. I'm going to actually align my B1 vector right in the direction in which the spider is moving, right? So now what that means is if I were to write RRS, I can simply say that RRS, if again B1 is in the direction of the spider's movement, all I need is that distance between the robot center and the spider. So again, we'll call that R, just as we did in our other approach. So we just write now that RRS is equal to R times B1. So now we're defining RRS in terms of reference frame B. So we can write out our position vector ROS is equal to UA1 plus VA2 plus RB1. And you can tell that already it's this equation is much shorter, right, than when we calculated everything in terms of A1 and A2. Before moving on to calculating the velocity, I just want to take a quick second and demonstrate that even though we use two different approaches, and right now it might look like our position vectors are different from one another, they are in fact the same. And that's because if you remember from one of the prior videos that we can write B1 in terms of A1 and A2. So B1 is equal to cosine theta A1 plus sine theta A2. And we can plug B1 into that equation there. And ultimately we'll get ROS is equal to U A1 plus V A2 plus R cosine of theta A1 plus R sine of theta A2, right? And so now this answer here is the exact same answer as we got using the other approach. And this should not come as a surprise, and that's because, I mean, this is the same position vector, right? And we must get the same answer regardless of what method we use. So I just wanted to emphasize that. Okay, so now we're going to calculate the velocity. of point S in frame A, just how we've done before. We take the time derivative of our position vector in frame A, and I'm going to write our position vector, right? Remember we had two different approaches, two different versions. We're going to use the one where we have two different reference frames used. So where we have R, B1. And so we have to take the time derivative in frame A, and so that's very straightforward if we are simply looking at the first two terms, so UA1 plus VA2. However, if we take the time derivative of RB1 in frame A, this is not straightforward. So just to flesh out what we can, we now have U dot A1 plus V dot A2 plus our troubling term here. I'll just highlight it again. So there's two approaches or two ways now that you can handle this term. The first approach is to use what's called as the magic formula. However, we have not gotten to that. That is for the next video. So we're going to skip that approach at the moment. And we're just going to move on to approach 2, which is to rewrite B1 in terms of A1 and A2. Right? Basically what we did just a moment ago. So we know that B1 is equal to cosine theta A1 plus sine theta A2, so we can plug that in there. Now we can write this as U dot A1 plus V dot A2 plus the time derivative of R cosine theta A1 plus R sine theta A2, all in frame A. And again, now that everything is written in terms of the A1 and A2 unit vectors, we can easily take this derivative. So we have, just writing this out again, U dot A1 plus V dot A2 plus R dot cosine theta minus R theta dot sine theta A1 plus R dot sine theta plus R theta dot cosine theta A2. And now if you were to go back and look at your notes, so either your homework solutions or how we solved this in class, you would find that this is identical to what we, how we solved this problem before. And in fact, it almost begs the question, well, you know what, if you're just going to use this second approach, you're just going to substitute this equation in here for B1, then why did we even bother using two reference frames? Right? Why didn't we just stick with writing everything in terms of A1 and A2 to begin with? And that is a very, very fair point. I can't see the advantage. However, what you'll see in the next video is that I can introduce what's called a magic formula. And this magic formula will allow us to take this derivative, right? So we can take the derivative of this vector with respect to frame A, even though it's written in terms of frame B. And we can continue to exploit the simplicity that's afforded to us through the use of multiple vectors.